Good morning, good afternoon, good evening. Today we're going to be talking about the Diels-Alder reaction. In this experiment, basically we have a conjugated diene. This is the principal, plus an alkene. An alkene means you just need one double bond. It doesn't matter if you have more. But in the conjugated diene, you have to have an alternation. That's to say, double bond, single bond, double bond. That's all you need. So we'll call it number 1, number 2, number 3, number 4, number 5, and number 6. Now remember, of course, the bond is made out of 2 electrons. So we are going to put 1 electron here, 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 and 1 electron there. So number 1 and 5 go together. Number 4 and number 6 go together. And then number 2 and 3 go together. So what you end up always is a 5-membered ring. So we have a 1, 2, 3, 4, 5, and 6. So 1 goes with 5, 4 goes with 6, and then 2 and 3 have a pi bond. You notice here then, of course, that we have here, if you want to count them, you have 1, 2, 3 bonds that are single, and 2 double bonds, that's 5 bonds, and you have 2 more here, a single and a pi bond, so that's a total of 7 bonds, and we have 6 bonds here, and that's 7. So we can account for the number of bonds and the electrons. So again, we have a conjugated diene, which means you have an alternation between a double bond and a single bond, and you have an alkene, which involves a just pi bond. It doesn't really matter what follows. Now, what you realize here is that you break here, 2 pi break, 2 pi bonds, and 1 pi bond here, right? You broke this bond and this bond and this bond. And what you created is you created 2 sigma bonds and 1 pi bond. So what you end up with then is a situation where you break 3 pi bonds and you're creating 2 sigma and 1 pi. Now we know the strength of sigma bond is stronger, higher than the strength of pi bond, which means now that in order to break a sigma bond, you need more energy. To break, we break 3 pi bonds, okay, which if it is about, say, if 1 pi bond is about 80 kilocalories per mole, and 1 sigma bond is about 100 kilocalories per mole. This means from the left hand side I need to break 3 pi bonds, so it's 3 times 80, that's 240 kilocalories per mole. And what you do is you create 2 sigma bonds, that's 2 times 100, plus 1 times 80, so you create 280 kilocalories per mole, which means the reaction will end up with 40 kilocalories per mole, which is an exothermic reaction. Okay? Okay, so then now what is going to happen then is, in our experiment, we are going to be working on cyclopentadiene plus maleic anhydride, and then we have 1, 2, 3, 4, 5, and 6. Again, we make a 6-membered ring. 1, 2, 3, 4, 5, and 6. 2 and 3 is always a pi bond. 1 is connected to 5, but 5 is also connected to 6 via this. And so therefore, as a result then, what you end up with is an exothermic reaction. However, cyclopentadiene by itself also reacts with itself if they are together in a liquid form. And you know, of course, in the liquid form, molecules are very close to each other. So what we have here is 1, 2, 3, and 4, 5, and 6. So what happens is when you purchase cyclopentadiene, you don't purchase cyclopentadiene itself. You purchase 1, 2, 3, 4, 5, and 6. 1 and 4 are connected. And I'm not talking about stereochemistry here, leave it alone. And then 5 and 6 are connected with 3 carbons, 1 carbon, 2 carbons, 3 carbons. And the first one is a single bond, then we have a double bond here. Which means now that what you end up with is always a 6-membered ring, and then you have the other connections. Notice, of course, that cyclopentadiene by itself will not exist in this form. It will always exist in this form. So how can you create this one? If from A to B is exothermic, this means B to A will have to be endothermic. This means here you have plus, say, delta H. So to go back now, what you're going to do is, if you apply heat, you will get the pure cyclopentadiene. And so therefore, in this case, then what do we do? What we're going to be doing is we're going to be getting the product that is called dicyclopentadiene. And we are going to apply heat to that. We're going to fractionally distill it. No need to pack the distilling column. And then what is going to happen then is we will distill off the pure cyclopentadiene. The boiling point of cyclopentadiene is approximately about 40 degrees or 40 to 50 degrees. The boiling point of this is approximately 160 degrees. But when you apply heat then, what you do is you revert to this. And so therefore, since the temperature is going to be higher than its boiling point, is going to be distilled off, and we have to collect it in ice. Once we collect it in ice, we will react it with, this is again cyclopentadiene, and we will react it to maleic anhydride. So we will mix the cyclopentadiene, which we've freshly distilled, with maleic anhydride, and we will be getting a product. Notice now that I don't talk too much about the stereochemistry. That's for the lecture part. So what we're going to be doing today, we're going to be doing actually the reverse or retro Diels-Alder reaction, which means you go from the product of the Diels-Alder product, on the product you go back to the reactant, which is the conjugated diene, and then once this is formed, we will react it with maleic anhydride, and we have the Diels-Alder. So we approach this reaction via 2 ways: creating the conjugated diene, and then reacting it with a alkene, or as we call it, dienophile. Okay, and dienophile comes out of 2 words, diene, and the word philo, which in ancient Greek meant to love, and in modern Greek it means to kiss. So I guess this is a deterioration of morals. Okay, so basically that's how it is. Any questions that you have, we will discuss them as we go along. Okay, so what we're going to do first is a retro. Okay, so here we go. Okay, now what we need to do here, first of all, again, this is the dimer, the dicyclopentadiene, which is this one. What we're going to do now is we're going to take this dicyclopentadiene and we're going to pour it in here. Notice what I did now in the lab. In the lab, we never have the round bottom flask sitting on the heating mantle. We always use a funnel, because if you put it on the heating mantle and accidentally you spill some of it, you know the heating mantle is going to get warmer, and so all the fumes are going to come out, and that's not very healthy. So whenever we pour anything to the liquid, we always keep it away from the heating mantle, and that's something you always remember. Okay, now I added it, and what I'm going to do is I'm going to stick it in here. Okay, make sure that I stick it, because you notice here I leave the heating mantle excuse me, the heating mantle a little bit higher, because when I want to stop it, what I do is I have to drop the heating mantle down. If I don't clamp this one very well, you know, Newton's law of gravity applies even in organic chemistry. Okay, so the whole thing is going to fall down and we're going to have a disaster. So far so good. Okay, now we do the and we use the grease, just a little bit of it, not too much. Put it here, 1, 2, put it here, You don't have to go around it. You just put two spots and then rotate it. That's good enough. Okay, what did I forget to put in? Boiling chips, right? So we put a couple of boiling chips. You don't need too many. 2 or 3 of them will be more than adequate. Okay? Okay? And then what I have to do now is I have to put the, continue the building up the setup. And again, 1, 2, put it here this way and rotate it. And this is the easy way of doing it instead of going around and around and around and having too much grease. Okay, we don't need to pack this column because the distance is long enough for the separation to take place. Now we need to put the thermometer. Now we have here the thermometer, we have to plug it in here. So you never hold it this way because if you hold it this way it's going to break in your hand. What you do is you hold it this way and slowly insert it. Okay? I have seen a lot of things taking place. So, and accidents. So now you put it over here. Now remember now, what did I forget? I forgot to put the grease again, right? So we put a little bit of the grease here. 1, 2, put it here, rotate it. Now the position of the thermometer is not the right one, yes? Why? Because the top of the mercury bulb has to be at the bottom of the connecting adapter. Do we see that? We just put it this way. You see that? It cannot be this way. Sorry. Cannot be this way. Cannot be this way. It has to be just about there. All right. So far so good. Now we remember. Now this one has to be very well clamped. Okay. Now the next thing we have to do is we have to put the regular condenser. Notice here that when we do a fractional distillation, we prefer to have always the thicker condenser, right, which has a larger diameter, and then this one has to have the lower diameter. Now, of course, in the fractional distillation apparatus, the fractionating column has to be perpendicular. It cannot be like the Tower of Pisa this way. All right, it has to be straight up. Okay. Okay. I hope I didn't offend any Italians here. All right. Now we have to put this thing here. Again, what did I do? I forgot to put the grease, right? So we put the grease here again. 1, 2. Don't put it here this way because then sometimes it gets stuck. Your finger gets stuck, and then I don't have time to take you to the hospital. All right. So now we have it this way. Now what's the problem that we have here? The problem that we have here is that this one, Newton's law of gravity applies, and this is going to fall down. So what do we need to do? We need to use rubber bands. Now the rubber bands, we prefer to, in this case, because this is going to be the hotter part, we like to have more than rubber band for several reasons. A, one of the rubber bands, if you put only one, it may break, either because it's weak or because it's too hot. So we like to have more than one rubber band. So we put it this way and this way. Are we in agreement here? Now we rotate it this way, so we are in shape. Now this is not going to fall because hopefully the rubber bands are brand new and they're going to be all right. So far so good. Okay, what's the next thing? The next thing we have to do is we put the vacuum adapter. What's the problem that we have with the vacuum adapter? It's going to fall down again. So what do we need to do is we need to put again rubber bands. We do it this way. So this way we hold it tight. Okay. Now you have to have as few clamps as possible because that creates strain. Notice here then that when the liquid comes up here, its boiling point maybe it's high. But over here, again, it has condensed. And so therefore, you don't need to put grease in necessarily here because it's not going to get stuck. We put grease because when the two pieces of glassware get very hot, they expand. And then when they cool, they just get stuck together and we have a problem. Now here, we have to put a round bottom flask. But again, Newton's law of gravity applies, right? So what we need to do is we need to, here we go, and then we tighten it. All right? So now the whole thing is pretty safe. All right? Notice now the following, and if I bring this down in the long run, because I tighten it here, okay, and I tighten these two also, everything is safe. Anyway, so here we go. Now we're going to be distilling the cyclopentadiene, and we will be collecting it, and then we are going to react it with the maleic anhydride. Now there is a problem here. The problem is that when we distill the cyclopentadiene that's formed here will start reacting with itself again, and we go back to what we had. So then what we do is we need to slow down the dimerization, which means a reaction of one cyclopentadiene with another one. So how would you do that? What we do is we have to collect it in ice, and we collect it in ice. Now remember now, for every 10-degree difference, if you increase the temperature by 10 degrees, the reaction rate gets doubled. So if the temperature outside now is, say, 30 degrees, and you collect it at 0, what happens now is the rate will go down by about 1/8. You collect your cyclopentadiene, and then you will react it with maleic anhydride, and you will eventually finish up with the product. Now notice now that the cyclopentadiene and the maleic anhydride will react to give you this product, which is a white precipitate. The maleic anhydride, as you read in your lab manual, will be dissolved in a solvent, which is PET ether and ethyl acetate, and then when these two react, the precipitate of the maleic anhydride will come out. Okay, so this is what we're going to be doing now for this experiment. And we're not going to mix it together, but you will basically, you realize what the process is, and that's how it is going to be. You have in your lab manual, at the end you have several questions. Try to work them out using this 1, 2, 3, 4, 5, and 6, and try to figure out what the products are. Now again, you can also, going back again to the lecture, I hope your lecture professor doesn't get mad at me, but if I have, for instance, a situation like this, this is my product, okay? So the question is, what are the reactants? Now remember, now we have 1, 2, 3, 4. 2 and 3 have to be a double bond, okay? And 1 is connected to 5, and 4 is connected to 6. Now what is going to happen now is that you, in order to make this, to go backwards, you have to break this bond, you have to break this bond. So you finish up with 1, 2, 3, 4 double bond here, and we have 5 and 6. But remember now, there is an extra double bond here, an extra pi bond. So what we do then is we have to have another pi bond. Okay?